Welcome to the deep dive. Today, we're tackling quite a beast of a survey paper.
Yeah, this one's dense.
It is. On the landscape of spoken language models. A comprehensive survey. Basically, think of it as your quick guide to understanding the state of the art in SLMs.
Spoken language models, right?
Exactly. It's the tech letting AI understand and, well, generate speech much better now. Kind of like the jump we saw with text LLMs.
And the AI community is definitely buzzing about it, this survey. It's like our map through the territory.
Right. So for anyone needing the super quick version, maybe for a short clip.
Okay, the nutshell version. This paper breaks down the whole SLM field. It looks at them by architecture, like, are they purely speech-based?
Or speech.
And text. Exactly. Or maybe text models that have been made, speech-aware. It covers how they're trained, how we test them.
And crucially, the big challenges and where things might go next.
Yeah, the authors really focus on three main types. Pure SLMs, just modeling speech patterns.
Right.
Speech plus text SLMs, juggling both spoken and written forms.
Right.
And these speech-aware text LMs, which kind of cleverly use existing text models to handle speech input.
So if you're out there, an AI researcher, an ML engineer, why does this matter now?
Well, SLMs could genuinely change how we interact with computers, really change it.
Like truly natural conversations, where the AI gets the words and the tone.
Potentially, yeah. And this survey gives you that essential overview of a field that's honestly still moving incredibly fast.
So understanding this landscape is key if you want to stay ahead or even just keep up.
Absolutely. And in this deep dive, we're going to unpack this survey, pull out the key bits.
We'll look at the architectures, right? The different kinds of encoders, decoders.
Yep. Training strategies, too. The pre-training, the post-training fine-tuning.
We'll touch on some example models, how they fit into dialogue systems, and the benchmarks used to evaluate them.
Sounds like a plan. Let's jump in.
Okay, so first up, architecture. What's the kind of basic blueprint that the survey says most SLMs follow, despite all the variety?
Well, what's interesting is that underneath, they share a core idea. The survey points out most SLMs take speech, text, or, both as input.
And output speech, text, or both.
Exactly. The key thing is, at least one part of that input-output involves spoken language. Figure 1 in the paper actually shows this visually, the different combos.
Right, so if the input is text, it goes through a text adapter, usually just an embedding layer, pretty standard. But if it's the raw speech waveform, first step is a speech encoder. Transforms it into a sequence of representations.
And these can be continuous vectors or discrete tokens. We'll probably get into that distinction more.
Yeah. Then there's this speech modality adapter step. What's that doing?
The modality adapter. It's really, really important. It takes what the speech encoder gives it and processes it further.
To make it compatible with the next stage.
Pretty much. To make it play nicely with the sequence model that follows. It's like a translator, Taking the raw speech language and turning it into something the core LM understands often deals with the length differences between speech and text too.
Got it. And after these adapters, the representations may be adapted text, maybe adapted speech, maybe both get fed into the sequence model.
Yeah.
The brain, you called it?
Yeah, the core engine.
And this generates outputs autoregressively. Can you break that down a bit?
Sure. Autoregressive just means it generates step by step. Like it predicts the next thing in the sequence based on everything that came before it.
So one token or representation at a time?
Exactly. It generates a piece, adds it to the history, and uses that new history to predict the next piece. Builds the output sequentially.
And the output type depends on the SLM flavor, right?
Right. Pure speech LMs spit out more speech representations, which then need a speech decoder to become a waveform again.
Okay.
Speech-aware text LMs. They take adapted speech and text, maybe, and generate text output.
And the speech plus text models.
They can potentially produce both speech and text together. And the survey notes that these main parts, encoder, decoder, sequence model, are often pre-trained separately.
Leveraging existing models.
Exactly. But that modality adapter, often trained from scratch, sometimes along with fine-tuning the sequence model. It's quite modular, which lets researchers mix and match powerful components.
Okay, let's zoom in on the speech encoder then. Text is easy, you tokenize words. Speech is, well, continuous. How do you get those first meaningful representations?
Yeah, that's the job of the speech encoder, which they detail in Figure 2. Its main goal is turning that messy audio waveform into something structured for the sequence model.
First stage.
Often a speech representation model. This pulls out continuous feature vectors, think spectrograms maybe, or increasingly these hidden representations from really powerful self-supervised learning models.
Like Wave2Vec 2.0, Hubert.
Exactly those. Or even supervised models like Whisper, or these neural audio codec models like SoundStream. Lots of options there.
So that's continuous features. But the survey also mentioned discrete tokens. How do you get those from speech?
Right, discrete tokens. Think of them like the speech version of words or subwords. You're basically quantizing or bucketing those continuous features into a set sequence of distinct units.
Like a vocabulary for sounds.
Kind of. The survey groups them mainly into phonetic tokens and audio codec tokens.
Phonetic tokens.
Usually derived from the continuous outputs of those self-supervised models you cluster or quantize them. They capture a lot of the linguistic content, what's being said. They correlate pretty well with phonetic sounds.
So early models used these like pseudo-text?
Yeah, models like GSLM did exactly that, treated them almost like text representing the speech content.
Okay, so phonetic tokens are about the what? What about the audio codec tokens?
And more about the how, it's said, capturing more acoustic detail. They come from these neural audio codec models, originally made for compressing audio efficiently.
For storage and stuff.
Right. But it turns out their intermediate discrete codes are super useful as tokens for SLMs, especially if you want to keep the speaker's voice, the emotion, the acoustic nuances.
So those codec models have an encoder, a quantizer, and a decoder for reconstruction.
Typically, yes. The quantizer part gives you the discrete tokens we need for the SLM.
Feels like a key trade-off here. Phonetic tokens for the meaning, audio codec tokens for the sound quality and character.
That's a great way to put it. Early SLMs often use phonetic tokens for understanding tasks because they tend to strip out speaker identity.
But now audio codec tokens are getting more popular for generation.
Definitely, especially where you need that richness speaker voice, paralinguistics, and people are actively researching better ways to make and evaluate all these tokens, looking at bit rates, quality, everything.
Okay, so we have these sequences, features, or tokens, but then the survey mentions temporal compression in the encoder. Why is that needed? Speech sequences are long.
Very long, yeah. Even after tokenizing, the sequences can be huge because audio has such a high sampling rate compared to text. Processing that directly is computationally heavy.
So compression shrinks the sequence?
That's the goal.
Yeah.
Simple methods exist, like deduplication, merging identical tokens that repeat.
But that loses timing info.
It can, yeah. Which is why some models use multi-stream approaches or try to predict duration separately. Another way is borrowing from text processing using something like byte pair encoding, BPE, on the discrete tokens.
To find common sound patterns and merge them.
Exactly, creating speech subtokens, effectively.
Okay, encoder done, maybe compressed. Then comes that speech modality adapter again. How does it bridge the gap to the sequence model? What are the common methods?
Right, the adapter aligns the encoder output with what the sequence model expects. Especially crucial if they were pre-trained separately and have different dimensions or sequence lengths.
So if the sequence isn't too long.
If it's not too long, maybe after compression, sometimes a simple linear layer works. Just projecting the speech representation into the sequence model's embedding space.
Like adding new words, the speech tokens, to the model's vocabulary.
You can think of it that way, especially with discrete tokens.
And what if the speech sequence is much longer, like with continuous features often are?
Then the adapter usually needs to shorten the sequence too. Common ways are using CNNs with strides that downsamples while trying to keep temporal info.
Or just pooling.
Simpler pooling layers, yeah. Or another interesting one is using CTC connectionist temporal classification.
From speech recognition?
Exactly. Here, it can compress the speech representation based on the recognized phonetic units, kind of highlighting the linguistically important bits.
The survey also mentions Q-former and A-LineFormer as more sophisticated adapters.
Yeah, they're a bit more complex. Q-former uses learnable queries that interact with the whole speech sequence via cross-attention.
To distill it down.
Right, into a fixed-length representation, which is handy for sequence models expecting consistent input size. A-LineFormer builds on that, adding a CTC compressor with the Q-former.
And that combo worked well.
Apparently, yeah. The researchers found it gave impressive zero-shot instruction following for speech QA, even better than Q-former alone sometimes.
It's fascinating how many ways people are trying to connect these speech and text worlds. So after the adapter, we hit the sequence model, the core. The survey says generating speech tokens isn't quite the same as text tokens, especially if you have multiple types of speech tokens.
That's a really key point. Text is usually one stream of tokens. But audio, You might have coarse tokens for broad sounds and finer tokens for acoustic details. That opens up hierarchical generation. Figure 3 shows some ways to do this.
Okay, let's walk through them first. Coarse first, then fine-grained. How's that work?
So the model first predicts the high-level coarse tokens for the whole sequence. Then it generates the finer-grained detailed tokens, but it uses those initial coarse tokens as guidance, conditioning on them.
Any examples?
AudioLM is a classic example. Predicts phonetic tokens, then the first layer of audio codec tokens based on those, then the next layer of codec tokens, and so on. Soundstorm and VL do similar things, but speed it up using non-autoregressive prediction at the finer levels.
Gotcha. Another strategy. Interleaved coarse and fine tokens. What's the idea there?
Here, you line up the different token types coarse, fine, maybe even finer along the timeline. For each time stack, the model predicts them sequentially. Coarse, then fine, then maybe finer still.
So within each moment.
Right. SpiritLM does this, using phonetic, pitch, and style tokens interleaved to get more expressive speech. It even mixes text tokens into that sequence.
Interesting. The survey also mentions temporal generation plus depth generation. Sounds complex.
It's a neat idea. You use a big transformer for the time dimension, the flow of speech over time.
Okay.
And then a smaller transformer head models the relationships between the different token layers within the same time step, the depth. So it models time and hierarchy kind of simultaneously.
Yeah.
UniAudio and Moshi use approaches like this.
And the last one mentioned is the delay pattern. How's that different?
With the delay pattern, there's a deliberate time lag. You generate the coarse tokens, wait maybe one or more steps, and then generate the finer tokens for that earlier step.
Why the delay?
It lets the model use future coarse tokens as context when generating the detailed ones for the current step. Gives it a kind of look ahead. PGSLM, for example, delays between phonetic tokens and expressive ones like pitch.
Okay, so these multi-stage methods sound like they can produce really good audio, but maybe slow things down.
Yeah, they add complexity and latency. The survey does mention a trend towards simplifying, maybe reducing the number of token layers needed.
Streamlining it.
Exactly. Maybe combining different token types into one unified tokenizer, or distilling phonetic info directly into the audio codec tokens.
Now, shifting slightly, some SLMs do text and speech hybrid generation. Why generate both text and speech tokens in one model?
The main driver is tapping into the huge knowledge base of pre-trained text models. They're usually trained on way more data than speech-only models.
So generating text first helps with accuracy.
Potentially, yeah. Generate text tokens as an intermediate step, then generate speech tokens conditioned on that text. Could improve factual accuracy, linguistic quality, plus it makes it easier to check if the content is right, separately from the speech synthesis quality during development.
But text and speech are structured so differently. Different lengths, different rates. How do hybrid models handle that mismatch?
That's the core challenge. The survey shows 4 main ways in Figure 4. One way, like Mini-Omni, adds padding tokens after the text sequence to stretch it out in time before generating speech.
Okay.
Another, like Llama Omni, adds fixed padding after each text token and also between speech tokens, trying to equalize lengths that way.
Seems a bit rigid.
Can be. Moshi is more dynamic.
Right.
It learns to insert a variable number of padding tokens between text tokens to better match the target speech length.
Smarter padding.
Kind of. And finally, models like SpiritLM or GLM for voice actually interleave speech and text tokens in one unified sequence. The alignment might be fixed beforehand or learned by another model.
Wow, lots of different approaches there. Okay, we've done encoding, sequence model. Last big piece is the speech decoder. Taking those representations continuous or tokenized and getting back to an actual audio waveform. What are the common ways?
Right, the decoder's job depends on what the sequence model gives it. If it's continuous acoustic features, you need a vocoder.
Like in standard text-to-speech.
Exactly, similar tech. If the model outputs phonetic tokens, you typically use a unit-based vocoder, often something like Hi-Fi Jan. These can also use extra info like predicted duration to make the speech sound better, especially if the tokens were compressed.
And if the SLM outputs audio codec tokens directly?
Then it's often simpler. You just use the decoder part of that pre-trained neural audio codec model. Plug and play, sometimes no extra training needed for the decoder itself.
Okay, that gives us a really solid picture of the architectural bits and pieces. Let's switch gears to how these complex beasts are actually trained. The survey splits it into pre-training and post-training, drawing a parallel to text LLMs.
Yeah, that's a useful way to think about it. Pre-training for SLMs is basically any training that isn't specifically aimed at making the model handle a huge range of downstream tasks directly.
So, like predicting the next token in text, or maybe continuing a chunk of unlabeled speech.
Exactly. Or even taking a pre-existing text LLM and training it a bit more on speech data before really integrating the speech part. The key is it's not directly targeting that universal instruction following capability yet.
And then post-training is about getting that general capability, handling different tasks based on instructions.
Precisely. That's where instruction tuning comes in. Training the model on data sets of speech paired with instructions and the desired outputs.
And things like RLHF.
Yeah, preference optimization like reinforcement learning from human feedback. That's also considered post-training, aligning the model with what humans prefer.
Let's dig into pre-training strategies specific to speech. The survey mentions pure speech pre-training. What's that look like?
Pure speech pre-training focuses on the model learning the patterns within speech itself. Usually you tokenize lots of unlabeled speech, then train an autoregressive model to predict the next speech token.
Using those self-supervised representations?
Absolutely. Those advances in self-supervised learning were fundamental here, giving high-quality representations to tokenize. GSLM pioneered this with discrete phonetic tokens. Later work tried adding prosody intonation, rhythm, or even using text LLMs to help model the spoken language better.
Okay. What about joint speech and text pre-training?
That uses datasets with aligned speech and text. Think audio recordings and their transcripts. The model learns to model both together, the joint probability.
Like those hybrid generation models we talked about.
Exactly. Interleaving the sequences or processing them as linked streams. The goal is learning the connections between spoken and written language.
The survey also mentions continual pre-training following text pre-training. What's the idea there?
That's taking a model already heavily pre-trained on text, a big text LLM, and then continuing its pre-training, but now on speech data.
To adapt it to speech.
Yeah, adapt it while hopefully keeping all that general knowledge and language skill from the text phase. It's common for SLMs built on text LLM foundations trying to boost their speech handling.
Now, besides these generative methods, there's also conditional pre-training. How's that used for SLMs?
It's less common than generative pre-training for SLMs, but you could start training an SLM from an existing conditional model, like a well-trained ASR system or a speech translation model.
Because they already know how to map speech to text for specific tasks.
Right. They provide a strong starting point if you want to build a more general instruction-following model that needs to understand spoken input for various tasks.
And for SLMs that mix pre-trained text LMs and speech encoders, the survey talks about aligning speech and text modalities during pre-training. How's that done?
There are implicit ways and explicit ways. Implicitly, you might use clever training goals, like the modal invariance trick, training the model to give similar outputs, whether the input is speech or it's text transcript.
Neat trick.
Or training on tasks like audio captioning. Turns out being good at that helps generalize to other speech understanding tasks. Explicit alignment is more direct, mapping speech features to the text transcript embeddings within the text LLM space, often by minimizing the distance between them.
Okay, moving to post-training. The survey mentions task-specific training.
Yeah.
How does that fit with the goal of a universal SLM?
Well, the big dream is often one model for everything via instructions. But some SLMs start with a more focused post-training phase, fine-tuning on a limited set of specific tasks first.
Using special tags, maybe?
Yeah, task-specific tags or tokens to signal the operation. Quinn Audio did some of this. This focus stage can then be followed by broader instruction tuning later to generalize better.
And we keep coming back to instruction tuning. Seems absolutely pivotal.
It really is. It borrows heavily from the success in text LLMs. You train the SLM on data like, here's some speech, here's an instruction about it, text or spoken, here's the right output.
And diversity helps generalization.
Hugely. Studies show that training on diverse, large enough instruction data sets lets SLMs handle tasks they never saw explicitly during training. The survey actually has good examples of instructions for different speech tasks.
Where does this instruction tuning data actually come from? Is it easy to get?
Not always easy, no. The survey lists a few ways it's created.
Yeah.
One is reformatting existing task data sets, like taking ASR data and adding natural language instructions instead of just labels.
Okay.
Another popular way is using LLMs themselves, like ChatGPT, to generate data. Give it a transcript, ask it to create relevant questions and answers about the speech.
Using AI to make training data for AI?
Pretty much. You can also synthesize speech instruction data using text-to-speech on existing text instruction data sets. And for more complex stuff, you can combine instructions for simpler tasks into harder, multi-step ones.
An important area now is ChatSLM training. How is training a spoken chatbot different?
Yeah, chat adds unique needs. It's interactive, conversational, needs different data, different strategies. Two main paths have emerged.
Path 1.
Start with a text LM that's already good at chat, and then basically teach it to understand spoken input. Speech-aware text LM for chat.
Path 2.
Build a pure speech LM or a speech plus text LM that can do speech in, speech out conversations directly.
How do you get the training data for these?
For the first approach, you might use a powerful text LML to generate text chats based on some speech, then fine-tune the SLM on that. For the second, often you use a high-quality TTS system to turn existing text dialogues into spoken ones.
Synthesizing conversations.
Right. Using real human conversations is ideal for naturalness, but that data is often messy, noisy, needs lots of cleaning.
Beyond these main strategies, the survey mentions other useful training details.
Yeah, practical stuff. Parameter efficient fine-tuning, PEFT, becoming super important.
Because these models are huge.
Exactly. PEFT means freezing most parameters and just tuning a small part, like the adapter, or adding small trainable modules. Makes training feasible. Progressive fine-tuning. Good for aligning speech and text. Start post-training with content tasks like ASR, then move to subtler things like emotion recognition. Conversational SLMs might start with cleaner audio, then fine-tune on real, messier conversations.
And avoiding forgetting old stuff.
Right, catastrophic forgetting. Experience replay helps mixing in some pre-training data during post-training. Finally, preference optimization, RLHF, or similar to fine-tune based on human feedback on quality.
We've covered a ton on architecture and training. Now, the survey looks at some actual representative models, grouping them. Pure speech, speech plus text, and speech-aware text.
Yeah, this part connects the dots, showing how those design choices play out in real models. Pure speech LMs, think GSLM, AudioLM, speech SSM, they're modeling speech statistics directly.
Okay.
Speech plus text LMs like Moshi, Spirit LM, Speech GPT, designed to handle both input and output in speech and text.
Bridge modalities.
And the speech-aware text LM.
Those usually bolt a speech encoder onto a text LM. Wave prompt, SEMO on N, Quen Audio, SLM, Wave LM, lots of examples. They take speech in, usually give text out. The survey has a big table and a timeline for more detail.
Yeah, Table 3 and figures text for anyone wanting the full catalog and history. The authors also mentioned that the big closed models from industry GPT-4o, Gemini, likely generalize these categories, but we don't know their exact architectures.
One really interesting niche the survey covers is duplex speech dialogue. That's beyond just turn-taking, right? Like a real phone call.
Exactly. Full duplex, where both people can talk and listen at the same time. That's way harder than standard turn-based voice AI.
What are the challenges there?
An SLM needs to figure out when the user's actually finished speaking so it can respond without interrupting awkwardly.
Bargain detection.
Right. It also needs to handle back channels, the yes, and other little vocal cues, and know what to do if the user interrupts it.
How are models tackling this? The survey mentions two architectures.
Yeah, two main approaches for end-to-end SLMs. First is the dual-channel approach.
Two ears.
Sort of. Separate input channels. One for listening to the user, one for its own output. Lets it process user speech while generating its own response, including deciding when to speak or stay silent. DGSLM and Moshi tried this.
And the second approach?
Time multiplexing. Uses a single audio channel, but has to rapidly switch between listening and speaking modes. The tricky part is when to switch.
How do they decide?
Could be simple, like fixed time slices for listening and speaking, or more complex, where the model predicts when to switch, maybe using special tokens in its output to signal my turn or your turn.
Fascinating. Okay, finally, evaluation. Critical part. How do we measure if these SLMs are any good? The survey says it's tricky with both speech and text involved.
Absolutely. SLMs are so varied. Dealing with both modalities means evaluation has to be multifaceted. Can't just use old single modality metrics alone. The survey groups methods into likelihood-based, generative, and trustworthiness evals.
Standard things like word error rate are still used, though.
They are, yeah, for specific tasks like ASR. But the survey focuses more on metrics suited to the unique nature of SLMs.
Let's start with likelihood-based evaluation. What do those tell us?
They mainly check how well the SLM captures the statistical patterns of natural speech. Often used in pre-training, especially for pure speech or speech plus text models.
How do they work?
Basically, give the model real human speech, see what probability it assigns. Compare that to the probability it gives a slightly messed up, less natural version. Metrics like SWOG or SPLIMP test lexical and syntactic understanding in speech.
And others look at prosody.
Yeah, ProSedit checks sensitivity to intonation and stress. The SEMN metrics look at non-word sounds, acoustic elements. A key point the survey makes is you need to evaluate both the initial tokenization and the language modeling part.
Okay. Then there are generative metrics, assessing the output quality.
Exactly. Relevant for all SLMs. If it generates speech, how natural does it sound? Clear? Consistent speaker voice? Does the sentiment match? Is the content coherent?
How do you measure that?
One way is generative perplexity. Generate speech, transcribe it to text, then measure the perplexity of that text using a big text LM. Task-based evaluation is also huge. Can it answer questions from speech? Follow spoken instructions. Use task-specific metrics there.
And there are benchmark suites now.
Yeah, big efforts here. Dynamic, Superb, AirBench, MMAU, AudioBench. They cover lots of speech audio tasks, often using powerful LLMs as judges for quality. Some newer ones like Style Talk or eChat 200 even focus specifically on style matching or emotion in generated speech.
And the last category, crucial nowadays, evaluating trustworthiness.
Super important. Since SLMs generate sequences of words, all the LLM concerns apply. Hallucinations, toxic content.
Factual errors.
Right, but speech adds more wrinkles. Audio hallucinations claiming sounds exist in audio when they don't. Toxicity is usually checked by transcribing the output first. Bias is a big one. Do models perform differently based on accent, demographic?
And deepfakes.
Huge concern. The ability to mimic voices convincingly means potential for misuse. So research into detecting synthetic audio is vital.
This has been incredibly insightful, really mapping out the SLM landscape thanks to this survey. So, to wrap up, what are the key takeaways, the big challenges, the exciting future bits for our technical audience? AI researchers, ML engineers listening in.
Well, the survey definitely highlights several big open questions, which means opportunities, right? Architecture is still a major one. What is the best way to represent speech? Discrete. Continuous. Which encoders work best?
And combining speech and text?
Still not fully solved. What's the best way? Fancy modality adapters.
Wow.
Tightly interleaved sequences. We need more clarity there. And efficiency, that's huge.
They're too big and slow now.
Many state-of-the-art ones are, yeah.
Yeah.
Hinders real-world use. So we need more research on compression, efficient architectures, definitely.
And training data sounds like a bottleneck, too.
Absolutely. A real lack of large-scale, public, high-quality data, especially for instruction tuning and chat systems. We need more open data sets. The survey also calls for more rigorous ablation studies and scaling experiments.
To really understand what works and why.
Exactly. Understand the impact of different choices and see what happens as we make these models even bigger.
And finally, challenges and future directions and evaluation.
Yeah, the benchmark landscape is still evolving fast. We need broader coverage of all the tasks SLMs might do and better standardized metrics, especially for generated speech quality.
Open source is an issue, too.
Limited availability of fully open models makes comparison and community research harder. Looking ahead, the survey really stresses inclusiveness, more languages, dialects, speech conditions, and, of course, safety and trustworthiness have to be paramount.
Tackling hallucinations, toxicity, bias, deepfakes.
All critical. Foundational work needed there.
Okay, so to leave you, our listeners, with a final thought. It seems really clear that SLMs have this massive potential, right, to fundamentally change how machines understand and interact using spoken language with all its richness. The challenges we talked about, they aren't really roadblocks, more like, well, exciting opportunities for innovation for everyone in the tech community listening.
Absolutely. Real chances to make breakthroughs.
So we hope you'll think about how your skills, your expertise, could help tackle these open questions and really push the boundaries in this incredibly fast-moving field. Thanks for joining us for this deep dive.